All right, this is lesson 4 from Unit 4, and today we're going to be talking about polynomial functions and how to write the functions if we are given the intercepts. So before we get into that, I wanted to reinforce this from last time and a little bit from the time before that. Using the x-intercepts determine the least possible degree of the polynomial. And we're also going to note if the degree is even or odd and the leading coefficient is positive or negative using the end behavior. So these first two, this degree and the leading coefficient, we get information about that by looking at what the two ends of the function are doing. In this case, both ends are doing the same thing. They're both increasing to positive infinity. So we know that it has to be an even degree function because both of the ends are the same, and the leading coefficient in this case, since they're both in the upper positive direction, the leading coefficient must be positive. Now, the least possible degree of this function, we'll use the intercepts to help us find. We see that there are two intercepts. That means this thing has to be at least a degree 2 polynomial. For this second one, we can see from the end behavior, one end is down, the other end is up high. We know that that means it has to be an odd degree polynomial. And the leading coefficient in this case, well, since it is overall decreasing, this right side is decreasing, we know that has to be negative. And the least possible degree of this function, well, I can see 3 x-intercepts, so it has to be at least degree 3. Final one. I look at this polynomial and I notice that this end is up high, this end is down low. It's got to be odd. But on the right-hand side, it is increasing, so that would be definitely a positive leading coefficient if we looked at the function. The least possible degree of this polynomial, well, we have only 2 intercepts, but it looks to me like both of those intercepts have some multiplicity. This one has multiplicity of at least 2. It's got to be an even number. And this terrace intercept over here has to have at least a multiplicity of 3. So the least possible degree of this polynomial would be 5. Again, you know, it's possible that this would be a higher degree. We just found the least possible degree. If this one instead had multiplicity of 5, which we can't really tell very well from the graph, maybe it's a 7, maybe it's a 9. We definitely know it's odd, and the least possible degree is 5. Okay. Today we're going to be writing polynomial functions if we know their zeros or their intercepts. So remember that if we know this is a cubic polynomial, so we're expecting degree 3, and it asks us to write it in standard form. So we know the zeros of the function are -1, -2, and +3. Well, each of those zeros will correspond to one of the factors of the polynomial. The 0, -1 corresponds to the factor x plus 1. The 0, -2 corresponds to the factor x plus 2, and the 0, 3 corresponds to the factor x minus 3. So this would be a polynomial function that has those indicated zeros, but it asks it for it to be in standard form. This is not in standard form right now. We have it in intercept form. Well, if we have something in intercept form and we want it in standard form, we simply need to multiply it out. So when we have 3 binomials, remember, typically we'll multiply 2 of them together. This would be x squared plus 2x plus x plus 2, or in other words, x squared plus 3x plus 2 if we combine those two like terms. And now that we have that multiplied out, we would multiply by our third factor, x minus 3. So we distribute that out, we get x to the third, 3x squared, and 2x. So I multiplied that x out. And now we need to distribute that negative 3 minus 3x squared minus 9x minus 6. That's negative 3x squared, negative 9x, negative 6. So if we combine our like terms, we have x to the third. In this case, we have 0x squared. Those two add up to 0. Minus 7x minus 6. And that is a cubic function in standard form that has zeros of negative 1, negative 2, and positive 3. So that's our first function. Here's the graph in case you wanted to look at it. Let me pull that up for you. So you have zeros, or x-intercepts, at negative 2, negative 1, and positive 3. So I actually have it typed in up here on this side in intercept form. I also typed in the function in standard form that we just calculated, and you can see that those two functions are exactly the same function. Now, this function g of x is not, or f of x is not the only function that has those intercepts. There are other functions. For example, this function also has those same zeros. It's just stretched by a factor of 2, but it has exactly the same intercepts, or exactly the same x-intercepts. We could multiply it by a half and have those same x-intercepts. We could reflect it. So there's actually an entire family of functions that has those intercepts. And so in a minute, we'll be talking about, when we do our next example, how to find a particular one of those. In this first example, it didn't specify which one we cared about. It just asks us to find a cubic polynomial. So any of the cubic polynomials that go through those intercepts would work. They're all just multiples of each other, though. So let's see how it works if we know a little bit more information about our function. For example, if we know the y-intercept. So this says, our example 2 says, write an equation for the cubic polynomial shown. We want to write both the intercept and standard forms. So we look at this function and we see that it has x-intercepts, or zeros, at negative 2, 3, and 7. Well, each of those zeros corresponds with one of the factors of the polynomial. Negative 2 corresponds to the factor x plus 2. 3 corresponds to the factor x minus 3. 7 corresponds to the factor x minus 7. This would be the factors of the polynomial. Let's multiply that out. If we multiply these two together, we get x squared. We have a positive 2x and a negative 3x, so that's a negative x minus 6. And we still want to multiply that by the x minus 7. So if we multiply this and distribute it, x to the third, x squared minus 6x. So that was distributing the x. Now we'll distribute the negative 7. That will be negative 7x squared, positive 7x, positive 42. That's just distributing the negative 7. So if we combine our like terms, we have x to the third minus 8x squared plus x plus 42. Now, this function definitely, that we have written right here, x to the third minus 8x squared, etc., definitely goes through these points. But we've talked about x-intercepts before. My function that I have written right now has a y-intercept of 42. If I plug 0 into my function, I have a y-intercept of 42. But the function shown here on the graph has a y-intercept of 0. 0, 6, sorry. So we need this equation right here. We need to adjust it so that it has a y-intercept of 6. Well, the way that we can adjust it, we can't just add a number or subtract a number, but what we can do is multiply that equation. We can stretch it. We can use a vertical stretch. In this case, we want this 42 to become a 6, so we want to multiply the whole function by 1/7, or some of you maybe were thinking that you would want to divide by 7, and multiplying by 1/7 is the same as dividing by 7. So we want to multiply that entire function, every single term, by that 1/7. And it is proper that you would want to distribute that. So the standard form of our equation, if we distribute that 1/7, would be 1/7 x to the third, 8/7 x squared. Don't make that hard. If it doesn't divide evenly by 7, just leave it in as an improper fraction there, as an 8/7. And then we would have 1/7 x. Again, it's fine to leave that in fraction form there, that coefficient. And then finally, that last one would be 1/7 times 42, and that gives us the 6 that we wanted. So that's the standard form of the equation. Intercept form would look similar. You still need that same stretch factor, 1/7 here, but intercept form, we would have our factors written. X plus 2, x minus 3, and x minus 7. So in both cases for that function, you do need to figure out what that vertical stretch is going to be for the function to get it to match. Otherwise, if we hadn't included that 1/7, the function would it would still go through those same intercepts, but it would be super, super stretched out, and we wouldn't even see that min and max on our coordinate system as shown. We'd have to zoom out. All right, let's do another example, example 3. The roots of a quartic polynomial function f of x are 0, 2/5, and -3 with multiplicity 2. The graph of the function also goes through the point 1, -18. What is the function? And we are going to write it in standard form. So first of all, it's a quartic polynomial, so we know that it's degree 4. And it has a list of zeros for us here, or roots of the function. Okay, so we have 0. Well, if one of the zeros is 0, or one of the roots is 0, the factor that goes with that is x. So that's our first factor. The next one, and this is a little bit tricky, so I'm going to do a little scratch work down here. 2/5 is our 0. So you could, if you want, write it as x minus 2/5. There's nothing wrong with that per se, but it can get a little tricky multiplying it out with that fraction in a minute when we multiply it out. So another way to write that factor would be 5x minus 2. Remember, when we have a factor like 3x plus 4, if we want to find the 0 that goes with it, it ends up being a fraction. So if you have a fraction as your 0, think about how to turn it back into a factor where the x has a coefficient. So I'm going to use the factor in this case 5x minus 2, and we'll practice finding the factors for those sorts of zeros a little bit more in our bell work next time, and you'll get real good at it. And then finally, so that was this 0, and finally it says we have a 0 at -3, so that's an x plus 3 factor, and it says this one has a multiplicity of 2. So we have that factor twice, and we can show that with the power squared. Okay, well, let's go ahead and put this into standard form as is, and then we can check that point 1, -18. Well, we could distribute this x into here. That gives us 5x squared minus 2x. And this x plus 3 squared, remember that just means times it by itself. And if we do that, we have an x squared. We have a positive 3x and a positive 3x. That's a 6x. And then finally we have a 9. Okay, so we're almost there. We just need to finish multiplying this out. That's a 5x to the 4th power, a 30x to the 3rd power, 45x squared. And we have a negative 2x to the 3rd power, a negative 12x squared, and then finally a negative 18x. So if we combine all of our terms that are alike, that would be a 33x squared minus 18x. Okay, so here's our potential function right now. This point 1, negative 18 is telling me if I substitute 1 in for x, I should get the answer negative 18. The thing that we're trying to calculate here is that we need to know what it's being stretched by. So let's go ahead and substitute this point into our equation. We have 1, negative 18, so x is 1 and y is negative 18. Negative 18 equals a times 5 times 1 to the 4th plus 28 times 1 to the 3rd plus 33 times 1 squared minus 18 times 1. So this whole part right here is just a number, and we can calculate that number. Let me grab my calculator and calculate it. And it's 48. So negative 18 is equal to a times, figure out what a is, what the stretch is. So we just want to divide by 48. So we get that a is equal to, and negative 18 over 48 is a fraction that we can reduce. And if we reduce that fraction, it's negative 3/8. They're both divisible by 6. So negative 3/8 is our stretch there. So if we want to write the function in standard form, we just need to distribute that stretch to each of those terms. So that would be negative 15 over 8, x to the 4th, negative 3/8 times 28 as a fraction would be, and it's a challenging one to reduce. Don't worry about exactly, I mean, you could think about that these are both divisible by 4, so that's a 7 over a 2, so it's a negative 21 over 2. This one is going to be negative 99 over 8. That one didn't reduce at all. And then finally, this last one's going to be positive 27 over 4x. So here is the function. Now that is a very, very challenging one. It's fine. It's definitely more challenging than just having to adapt to a y-intercept. Okay, last one. Here we go. Write an equation for the cubic function shown. So we have an intercept of negative 2, and we have an intercept of positive 2. Now we have to note this behavior right here. It touches and turns around. That tells me that this has a multiplicity of 2, and it's a cubic function, so we know we should have three roots. So if we write the factors for the function, they're going to be x plus 2. That's having multiplicity 2. Sometimes I'll write that with a squared symbol, but I'm going to write it out this time. And the other one is x minus 2. Now the reason that I wrote it out is because I was thinking that these two would be much easier to multiply together first, and then we can multiply that result by that other x plus 2. Now you could have done it the other way. It's just that I happened to notice that x plus 2 times x minus 2, that is a sum and difference of factors, and that's going to be an x squared minus 4. So that's a really easy one to multiply, so I kind of thought that we could multiply that one first. Now we can multiply it by the factor x plus 2, so we get x to the third plus 2x squared minus 4x minus 8. X to the third, 2x squared minus 4x minus 8. So now what we just need to check is, does this function have the y-intercept I want it to have? We've got to figure out what we would want to multiply by. Well, right now it has an intercept of -8. The function shown has a y-intercept of -4, so it looks like we just want to multiply that whole function by half. And we should distribute that 1/2 x to the third. Half of 2x squared is just a 1x squared. A half of 4x is -2x, and then finally we have -4. So here is our function in standard form that has a y-intercept of -4, and it has zeros as shown on the graph. Okay, I had 2 practice ones for you to work on in class. I'm not going to include those in the video. So that is it for the video. If you need some help with this concept, just let me know. Come in for some extra help before school, after school, or at lunch. Thank you.